Hi everyone, in this research presentation we are going to talk about scaling up anonymous communication networks thanks to the usage of nanopayment channels. So this research is a collaboration between the UC Louvain crypto group with myself and my thesis advisors Olivier Pereira, with Rice University members Tienan Din and Dan Wallach. So the goal of our research is to help anonymous communication networks such as Tor to incentive relay deployment in useful place in the world. So let's start with a bit of background. The Tor is a volunteer-based distributed network where everyone can run a relay to help people getting some level of anonymous internet connections. And to connect to a website using Tor, clients can use the Tor browser or any other software packaging Tor to build a path that we call a circuit through available relays in the network. And Tor threat model assumes a local adversary that can control a part of the network. It can be relays, it can be autonomous systems, internet service providers, or even a full country. So that's why we need incentives to run those relays in as most diverse place as possible, in order to increase the chance to avoid adversaries or to increase the cost to control a sufficient large fraction of the network. So several works in the past try to achieve that goal by offering premium bandwidth, which would be a small advantage in network speed compared to non-premium users. And different designs reflecting different ideologies have been proposed. And in summary, it has been difficult to obtain a design that meets a trifecta of constraints: anonymity, payment security, and efficiency. So the idea is that you don't want anyone able to cheat to get premium bandwidths. You want secure ownership of funds, you want secure balance, you want network efficiency, means that the incentive schemes should not impact the network throughput, and so on. But solving the technical problems is not the only difficulty. You also have the social issues surrounding incentives mechanism. For example, consequences of mixing relay operators with different motivations, or simply setting a price over someone else's contribution, may have adverse effects. And you may find some explanation inside this blog post or inside our paper. So those problems we consider them in our design by giving a monetary payment system as flexible as possible, but which can then be constrained by the authority through a kind of programmable monetary policy. So in our design we have a central pot that collects taxes of the direct payment made in the network. The incentive mechanism can then be tuned by setting the taxes amount, by designing a distribution policy of those taxes, by constraining the ledger, and by tuning the premium bandwidth advantage. So by answering this set of questions, we may really shape the incentive to something that we may think that could be the right solution. So let's talk about our technical design now. So one of the components of our incentive design is payment channels. So channels allow to convey payments to someone else without interacting with the ledger. So this design helps with, in fact, two of the technical challenges. It helps with efficiency because it improves scalability by avoiding everyone to connect to a central entity. And it helps with protecting users' anonymity because it avoids to force the users to leak some information by the connections to the central entity as well. Yet payment channels does not provide an linkability between payments, which will be necessary if we want to maintain long-term anonymous relationship with relay through multiple circuits over time. And so to obtain a linkability at the payment layer, we use at starting point, Bolt, which is the anonymous versions of payment channels that is made possible with some nice cryptographic tricks. So Bolt helps us to have those long-term relationships on Tor, because so when receiving a payments, the relay will not be able to tell whether these payments is from the same user or another one. It can only tell if the payment is valid or not. But we still have some issues with Bolt, and to understand them, let's have a closer look to the protocol. So I've divided the set of Bolt protocols in 4 different parts. So the initializations allows to each party to set up their cryptographic material. The core protocol is composed of an established phase in which both party interacts with the ledger to escrow funds and obtain a valid wallet. The pay protocol consumes a part of the escrowed fund and updates both wallets of each party until all escrowed fund is consumed or the channel is closed. Then the channel closure is a three-way protocol, three-party protocol, in which the client first obtains a refund token, which contains the client's view of the channel, and send that view to the merchant, who's eventually running their side of the protocol, of the closure protocol, to finally enter the dispute resolution on the ledger. And this dispute allows to make the final balance between the two and update the wallets. And Bolt is a truly nice protocol, but the anonymous payment procedure is quite costly. In fact, it requires 2 RTTs between the parties, which wouldn't really allow us to implement any stream of payments within a Tor circuit to make some kind to allow clients to make payments for a few bytes, for example, or just for one page, one web page. Also, long-term relationships between potentially each Tor users and each relay does not scale very well, right? So for these reasons, we refactor the core protocol, and we make use of a trustless intermediary that is tasked to route payment trustlessly and maintain long-term relationships with the relays in behalf of the clients. Then we also replace the pay procedure by a set of nanopayments protocol that we designed to be in line with the requirements of anonymous networks such as Tor. So roughly speaking, the creation and closure of the nanopayment channel works like a Bolt pay operation. They are unlinkable to another nanopayment channel and create a stream of transparent nanopayments within a circuit. So you can see this as another level of indirection inside a micropayment channel. Now let's get a closer look to the set of nanopayment protocol. First we have the nanopayment setup, which assumes that we already run a Bolt establish phase to get a micropayment wallet. So the setup generates a hash chain from a random value and interacts with the intermediary to prove that the nanopayment channel is correctly set up. And then they basically try to protect each others against a misbehavior of the others with the channel refund and the wallet revocations. Then the nanopayment channel phase is a three-party protocol in which the client sends a nanopayment tokens which contains the last value of the hash chains computed at the nano setup. Then the relay set up their part of the channel with the intermediary, and this channel is also routed to the same value H0, which marks the successful establishment of the channel. Then we can finally pay, And we can pay as much as the length of the hash chain by revealing the next pre-image value. So the true beauty of this design is that the setup and establishment can be done preemptively to the usage of the circuit by the client. So it's an accordance of the current Tor design. So it means that secure and anonymous payments are achieved during the exchange of data by simply revealing and checking a single hash pre-image each time we want to pay. So finally, the nano-close operations is run at both parties to discuss with the intermediary and update the final balance of the micropayment wallet with all the nano payments made inside the Nanopayment channels. So now to integrate our protocol in Tor, we've designed a prototype that includes micropayment and nanopayment interactions with a new real type, the intermediary, which is only tasked to process payments and does not handle any user stream. We also had to design to make a prioritization design, and this prioritization design ended up to be a bit more complex than we initially expected. So we have two complementary prioritization methods. The first, that we call a local priority, is what most of our previous work did in the past. The idea is simply to choose which one of the next queues of bytes to flush to the network. And the second one, which is the circuit level priority mechanism, gives the maximum amount of data that that can be in flight within the circuit at a given time. And both approaches are complementary, and their efficiency depends on where congestion happens. So, for example, the current state of the network make the exit relay under pressure, which means that congestion happens mainly at the exit interface. And this has for effect to make local priority almost ineffective on average, and this is why we propose this kind of dual prioritization design that is effective depending on where the congestion happens. So now that we have covered the building blocks, let's move to the design evaluation itself. So our goal is to prove that we can deliver advantage to premium users while incurring minimal overhead on the whole network. And our methodology is the one ubiquitous to Tor research. We use a scaled-down version of the Tor network in Shadow, and what we want to do is to measure the overhead costs of the system. We want to measure the latency of the channel establishments and closure, and we want to observe the qualitative premium advantage. So first, our overhead experiments. We have all clients running Nanopayment channels when fetching web pages and small files. And we compare that to a baseline experiment in which none of the clients use Nanopayment channels. So we ran two trials, one in which we simulate all the network with access to multiple CPUs, and the payment processing code is deferred to another CPU each time, and one in which all the network run over a single core. This experiment is designed to try to observe the impact of our channel cryptography processing over the overall throughput in a worst-case context where everyone runs channels. So the intuition to explain the minimal overhead we observed here is simply that the channel AV operation happens outside of the data transfer window, because it happens when we open the channel and when we close it. Which means that we can engineer the implementation such that the priority is always over transferring bytes over the network, and when we have free cycle, we can pick the task of opening and closing channels over a given relay. So this second set of results is the latency analysis. The left one gives the time to establish the Nanopayment channel from the client's perspective, and the right one is my favorite result from this research. This graph displays a CDF of the time to first payment, with the 0 being the payment call to NanoPay, and the send being the actual the time of the actual sending of this nano payment to the network. And if we observe no discrepancy between the two lines, it means that the establishment, preemptive establishment, was perfect. So it means that as soon as we use the circuit, we were able to pay for the bytes that we receive. This graph shows the priority advantage, considering a quarter of the clients paying for premium bandwidth, with different parameters value applied for the local priority and the circuit level priority. So as you may observe, the tuning must be very cautious, because it's really possible to just degrade the performance of the non-premium user while not really improving the premium ones. So now let's conclude by discussing the difficult problem, which is how should we shape the monetary incentive. So with programmable monetary policy, we have in fact many possible options, and let's go through a few of them here. So first we have the benevolent ruler, for which we set the tax rate to 100% and will essentially turn the monetary incentive as to a revenue stream for centralized effort to improve the Tor network. The second one is crypto libertarians. We set low taxes and we let the market self-regulate with relays that are selling bandwidths to price of that choose for money. And we have in-kind rewards. In this idea, we try to imitate previous work in-kind, non-transferable and ticket-based transferability by limiting the number of on-ledger transactions to 0 or 1. Subsistence relaying is the idea to limit the direct income of relays for the cheapest locations area in the world, and compensate the relays that are located in other areas with tax redistributions. So for example, the $2 VPS from OVH will not get compensated by taxes, but the others that cost much more money in, for example, Africa, will get a lot of taxes from the pot. And we finally have decentralized count making, which is an altruistic form of money. So the idea here is to have relays to back up approved projects by the Tor project or the research community or the Tor community or in general. So with that, I'm done, and my future self will take questions. Thanks.